Hi everyone. In this lesson, we're going to go over the development of confidence intervals. Now, before we delve into our discussion about confidence intervals, we need to discuss what a point estimate is. So a point estimate is a single value, a point or a number, derived from a sample that's used to estimate a population parameter. For example, suppose you want to estimate the mean time it takes 14-year-old girls at your high school to run the 100-yard dash. So you take a sampling of 50 students at random, and you find that the mean time to run the 100-yard dash for your sample of 50 is 14.5. And also assume that the sample standard deviation is 2.6. Then we call the value 14.5 a point estimate for the true population mean mu. The population in this case being 14-year-old girls at your high school. And we can also call 2.6 a point estimate for the true population standard deviation sigma. Now in our example that we just discussed, the value 14.5 was just an estimate for the true population mean mu. In all likelihood, the value 14.5 is not going to be exactly equal to the true population mean mu. That would be rather unlikely to happen. So the question is, how confident can we be in this value 14.5? So what we would like to do is we would actually like to form an interval around 14.5. For example, maybe something like 14.1 to 14.9. You notice 14.5 is right in the middle between those two numbers. So we'd like to form an interval around our estimate so that we can say in some sense that we're 95% or 90% or 99% confident that the true population mean lies in this interval. So the question is, how do we do this? How do we form this interval? And what exactly do we mean to say that we're 95% confident the true population mean lies in the interval? So that's what we need to do. And that's what statistics and probability theory can do for us. Before we begin constructing confidence intervals, we first need to go over a few definitions. A confidence interval, as we've already mentioned, is a range of values constructed from your point estimates that the true population parameter is likely to occur within. So, for example, in our previous discussion, we had 14.1 up to 14.9. So the range of values from 14.1 to 14.9 would be considered our confidence interval. Now, a specified probability like 0.9 or 90%, 0.95 or 95%, or 0.99, 99%, is called your confidence level. That you can think of as being the likelihood that you have captured the true population parameter that you're estimating. So for example, in our previous discussion, we might say that we have a 95% confidence that the true population mean is between 14.1 and 14.9. Now, your confidence level can be adjusted. The most common ones are 90%, 95%, and 99%. But you can have confidence levels of 92% or 98% if you want. Now, in the next slide, we'll consider how the confidence level affects the width of your confidence interval. The next definition we have is that of the significance level. If you consider 1 minus your confidence level, for example, 1 minus 0.9, that would equal 0.1. That we would call a significance level. Or if we had a 95% confidence level, 95% corresponding to 0.95, 1 minus 0.95 would be 0.05, and that would be our significance level. Or if you consider a confidence level of 0.99, 1 minus 0.99 would be 0.01, and that would be the significance level corresponding to a 99% confidence level. We oftentimes denote the significance level by the symbol alpha, so keep that in mind. Now we also define our margin of error to be half of the width of our confidence interval. So the formula is simply the width of your confidence interval divided by 2. So for example, down here we have a picture of what a confidence interval might be. So you have your left-hand endpoint here, your right-hand endpoint here for your confidence interval. The margin of error is half of the distance from here to here. So as you see, we have it labeled here. This distance from the center to the right-hand endpoint, that would be your margin of error. Or from the left-hand endpoint to the center of your interval. So for example, in our previous discussion, if you had something like the left-hand endpoint being 14.1 and the right-hand endpoint being 14.9, then your margin of error would be half of the distance from 14.1 to 14.9, or 0.8 over 2, which is 0.4. So your margin of error here would be 0.4 if this were our confidence interval. Now, you'll notice that the confidence interval is constructed by taking your point estimate. For example, in the previous discussion we had, if this were 14.5, your confidence interval is your point estimate plus and minus your margin of error. So that's another formula that we'll use. Now here are some factors affecting a confidence interval. First of all, the sample size n affects the size of your confidence interval. In general, the larger the sample size n that is taken, the smaller the variation is going to be in your sample means. Recall the standard deviation for your sample means is sigma over root n, so you see as n is taken larger, the variation in your sample means gets smaller. So that means that it's more likely that your point estimate for the sample mean is going to be close to the true population mean. So in other words, the larger n is taken, the smaller your confidence interval can be. Or the smaller n is taken, the larger your confidence interval needs to be. Also, the population standard deviation will affect the size of confidence intervals. The larger the variation in the overall population, the wider the confidence interval will need to be in order to be confident that you've captured the true population mean. So the larger sigma, the larger your confidence interval, or the smaller sigma is, the smaller your confidence interval can be. And the confidence level also affects the width of your confidence interval. The higher the level of confidence, the wider your interval will need to be in order to be more confident that you've captured the true population mean inside your interval. So the higher your confidence level is, the larger your confidence interval needs to be. This statement should make sense intuitively. For example, if you think back to the 100-meter dash example, if you have a point estimate like 14.5 and you want to be 99.9% confident you've captured the true population mean, you need to have a pretty wide interval. But if you say you only want to be 80% confident, you can make that interval much more narrow. So the higher the degree of confidence, the larger your interval needs to be. And correspondingly, the lower your confidence level, the smaller you can make your confidence interval. Now, all of the statements above also hold for confidence intervals for other population parameters like the variance. We just discussed the population mean up here, but these are all true for other population parameters as well. Now, here are the types of confidence intervals that we're going to be covering in this module. We're going to consider confidence intervals for the mean, mu, when the population standard deviation is known, so when sigma is known. Now you might ask, well, why would we know sigma and not the mean mu? Well, we'll discuss some situations where that might be the case. And then we're going to take a look at confidence intervals for the mean mu when the population standard deviation is unknown. This is the more commonly used situation. And then we'll discuss confidence intervals for population proportions. For example, what proportion of people have green eyes? That would be a typical population proportion problem. And then we'll also look at confidence intervals for the variance and standard deviation. So let's begin by discussing case number 1. That's what we're going to derive our first formula for. Now we're almost ready to begin constructing our confidence interval for case 1. But before we begin, let's note one important thing about the standard normal distribution z. Take note that 95% of all z values will fall between negative 1.96 and positive 1.96 as we have illustrated down here. So down here we have our standard normal distribution, and right here we have the value negative 1.96. We call that negative z alpha over 2. And right here we have positive 1.96. That's positive z alpha over 2. Now for the standard normal distribution, 95% of your area is between these two numbers. And so the area in this tail is going to be 0.025, and the area in this tail is going to be 0.025. So the area in both tails is going to be 0.05. And now you notice how we label alpha to be the area in both tails, which in this picture is 0.05. And you see why we call these numbers z alpha over 2, because alpha divided by 2, with alpha being 0.05, would be 0.025. That's what the alpha over 2 is. So that's why we call this number z sub alpha over 2. Now, if you'd like to, you could verify that 95% of the area under the standard normal curve falls between these two numbers just by executing this command in Excel. This would give you the area to the left of positive 1.96. And so you see the area from here all the way back to negative infinity would be the area of this shaded region, which is 0.95, plus the area of this region, which is 0.025. And you can verify that when you evaluate this in Excel, you'll get 0.975, which is the area from here all the way back to negative infinity. And so the area out here would be 0.025. So take note of these important characteristics for the standard normal distribution N01. Now to begin our derivation for the formula for a confidence interval for a mean mu, with the standard deviation known. Suppose we have a population in which sigma is known, but the mean is not. For example, perhaps we have a machine that makes gears, and from previous observations we know what the mean is, and we know what the standard deviation is for the diameters of the gears being produced. Now suppose we make a change to the machine to adjust the diameter of the gear. So we make a change to adjust the diameters. Now we would expect that the mean is going to be affected because that's why we changed the machine setting, but it's reasonable to assume that the variation will not change. So you see, there are situations where we can assume that the standard deviation does not change and we can use previous values for it. Now what we want to do is we want to determine the mean diameter for the size of the gears being produced after we made the changes. So what we do is we take a sample of size n and we evaluate the mean as a point estimate. However, of course, the x bar is in all likelihood not going to be exactly equal to the true population mean, so we need to find a range of values around x bar, that's our confidence interval, where we can be confident in some sense that the true population mean lies in this range. That's exactly what we do when we construct a confidence interval. So how can we do this? Now let's take a look at the mathematical process that will give us a formula for confidence intervals. Now, by the central limit theorem, for n large enough, the z-scores given by x bar minus mu divided by sigma over root n, remember these are the z-scores for the sample means, these should be normally distributed n01 random variables. So these values will be normally distributed with a mean 0 and a standard deviation of 1. Now recall from our previous discussion that for n01 random variables, 95% of the z-scores will fall between these two numbers. So if we evaluated x bar many times, so we went out and we took many samples of size n, and we evaluated many of these numbers, and we tallied them up, then 95% of these numbers should satisfy this inequality right here. So you see 95% of these z-scores should be between negative 1.96 and positive 1.96. Now using a little bit of algebra, what we can do is we can isolate the mean, mu right here, the population mean, in between these two inequalities, and we would get this right here. Now, I'm not going to go through all the algebra there. It's not that hard. What you would do is you would multiply each term by this quantity. So you see, if we multiply this by sigma over root n, the middle by sigma over root n, this term by sigma over root n, that's where these terms are coming from, the 1.96 times sigma over root n. And then we would subtract x bar from each term and do a little bit more algebra, and we would end up with this inequality right here. So what this means is if we went out and evaluated, say, 100 of these x bars, and we calculated 100 of these intervals right here, then we would expect that 95% of the time the true population mean would be contained between these two numbers. And we call this our 95% confidence interval. And that's our formula right there. We've developed it. Now keep in mind we can develop confidence intervals at other confidence levels by changing the 1.96 right here. And we'll talk about that in another slide, but we can create 90% confidence intervals, 99% confidence intervals, and what's going to change in this formula here would be these values, 1.96. You see, because the cutoffs up here, negative 1.96 and positive 1.96, represented the values where 95% of the area underneath the standard normal curve is between these two numbers. So if we want a 90% confidence interval, well, these numbers would change, and we'll talk about that soon. Now here we're going to discuss how to properly interpret a confidence interval. So suppose you want to construct a 95% confidence interval for some population mean. Well, what does the 95% really mean? Well, for sake of argument, suppose you constructed 100 95% confidence intervals. So you constructed 100 of them. Well, what it means to be a 95% confidence interval then is you would expect about 95% of these, or 95 of them, to contain the true population mean. And then about 5 of them will not contain the true population mean. Now, it doesn't have to be exact because we're talking about probability. So you may have 94 of your 100 intervals containing the true population mean and 6 of them not containing the true population mean. Or you might have 96 containing the true population mean and 4 not containing the true population mean. So that's how you should properly interpret what a 95% confidence interval means. It means that if you were to go out and construct many 95% confidence intervals, about 95% of them would contain the true population mean, and 5% of them will not contain the true population mean. For example, we have a graphic illustrating this. Suppose that you constructed 20 95% confidence intervals for some population mean. Now, 95% of 20 is 19. So what that means is you would expect about 19 of your intervals to contain the true population mean, and about 1 of them to not contain the true population mean. For example, if you look at this graphic down here, right here we have a vertical number line. Here's the true population mean, and here are your 20 confidence intervals plotted along this vertical number line. So you notice this first confidence interval right here contains the true population mean. This one also contains the true population mean. And you see this one right here that we have circled in red, 1 out of 20, does not contain the true population mean. You see the true population mean is right here. So you see about 19 of them will contain the true population mean, and about 1 of them will not. Now once again, those numbers don't have to be exact, but that's what you can expect. Now here's something else to note for a 95% confidence interval. Before you construct your 95% confidence interval, you have a 95% chance, or a 0.95 probability, that your confidence interval will contain the true population mean. Now once you construct it, then we normally state this. We normally state that we are 95% confident that the true population mean lies between x and y, where x and y are the endpoints of your confidence interval. And so this is how you should interpret what a 95% confidence interval means, and how you should properly state that to your readers. So now we have developed this formula right here for a 95% confidence interval for a mean mu when your population standard deviation is known. That is very important. Now keep in mind one thing about this formula. The value 1.96 and negative 1.96, those correspond to a 95% confidence interval. If you wanted a confidence interval at the 90% level or the 99% level, you would need to change these two numbers. Now also keep in mind that these values 1.96 are denoted by Z alpha over 2, as we saw in a previous slide, where for a 95% confidence interval, alpha is 0.05 and alpha over 2 is 0.025. And what the value 0.025 represents, that's the area in the two tails of the normal distribution n0, 1, extending to the left of negative 1.96 and to the right of positive 1.96. Or correspondingly, between these two numbers underneath the standard normal distribution, the area is 0.95, the area between these two numbers. Now, if you wanted a confidence interval at the 90% level, you would need to change these numbers. And you can use this formula in Excel to calculate the new Z alpha over 2 values. So if you wanted a 90% confidence interval, your alpha would be 0.1. That's the area in the two tails. And you would type in, right down here we have it, negative norm.inv, that's inverse, parenthesis 0.05, that's alpha over 2, comma 0, comma 1, and you will get back 1.645. So this number would change to 1.645 for a 90% confidence interval. For a 99% confidence interval, your alpha would be 0.01. And you would use this formula right here to find Z alpha over 2 in that case. Notice 0.005, that's this number divided by 2. And you would get back 2.576. So that's what this number would change to if you wanted a 99% confidence interval. And you can have confidence intervals of levels in between these, of course, or less than 90%. You would just have to use this formula right here and decide what your alpha would be. For example, if you wanted a 98% confidence interval, well then your alpha would be 0.02 in that case. And you would just have to use this formula right here with this number being 0.02. And then you would get back your corresponding Z alpha over 2 value. That would go in place of the 1.96s up here. And here we have a summary for confidence intervals for a mean mu with the population standard deviation sigma known. So this is the formula that we use right here. This is our confidence interval. The x bar is your sample mean. The sigma is the known population standard deviation. N is the sample size you use when calculating the sample mean, x bar. And the Z alpha over 2, that is determined by your significance level, which keep in mind is 1 minus your confidence level. So for example, if you use a 95% confidence level, then your significance level is going to be 1 minus 0.95 or 0.05. And your Z alpha over 2 up here, you can find by typing this formula into Excel, where the alpha is your significance level. And remember, we do have common values for the Z alpha over 2 for a 90% confidence interval. The Z alpha over 2 is 1.645. For 95%, it's 1.96, and for 99%, it is 2.576, as we saw in the previous table. But for non-common values, you can use this formula to find what z alpha over 2 is. And then this term right here, the z alpha over 2 times sigma over root n, that is called your margin of error. Keep in mind that is half the width of your confidence interval. And this represents the value that you move to the left and right from your sample mean to form your confidence interval. So, for example, if this is x bar right here, the distance that you move to the right and to the left to form your confidence interval, this distance is this term right here, and that's called your margin of error, and it's denoted by E. So this is the E right here, that distance. That's the distance you move to the left and right to form your confidence interval here and here. So that's a quick summary of the formula that you'll use for a confidence interval for a mean mu when the population standard deviation sigma is known.